Okay, so today we're going to look at vector equations. So we've looked at simple matrices and operations with matrices. So now we're going to kind of put that aside a little bit and look at vectors. This is just kind of an introduction to vectors. In chapter 4, we'll go into more detail of what a vector is and how to work with them. Okay. So a vector is an ordered list of numbers for right now. A column vector is a vector with only one column. So we do this for ordered pairs. So we often use this for ordered pairs. Or the triples, etc. All right, so a column vector, column vector V is going to have components, I don't know, 1, comma, or 1, 2. So that just represents your ordered pair, okay? Or you could have an ordered triple. So if it was a column vector of ordered triples, then it would be 1, 2, 3, like that. So 3 values. All right, so vectors in R2, that means they're a real number, and the 2 represents the entries, like how many entries that you have. So it's going to be the set of all vectors with 2 entries. Okay, so this is going to be our real numbers. And then the 2 represents the number of entries. So that's a 2, or it could be R triple, so R3, so 3 entries. It could be R4. So this is the set of all points in a plane. And we could say plane E. All right, operations with vectors, same as matrices for right now. So same as matrices. So you can add the components. But if it's a column vector and you're trying to multiply, you're not going to be able to multiply because remember, if it's a 2 by 1, right? So if you have 2 rows and you have 1 column, then you can't multiply another 2 by 1, right? Because these 2 things have to match. So we're not going to be able to multiply these. All right, so take a second and see if you can look at these vectors here. So I wrote these as, these are bold right here. So you'll see me write it as a vector being bold there, or with the line at the top. So when I write it out, you'll see me with the line, but a lot of times when it's bold, that represents a vector as well. Okay. Okay. So I'm going to show you in GeoGebra. So it kind of helps a little bit just to kind of visualize it. So I inputted the column vectors here. So I inputted U there, so that purple or that pink one is going to be 2, 3. V right here is going to be my -1, 2, and that's going to be the green line. So it kind of shades it when we're highlighting it. And so now I'm going to add the two values together, and I get the component 1, 5, and then here if I'm going to add those together, I'm going to get the component -8, 2. All right, so if you see, so my pink right here, I can't write on this, I'm sorry, but my pink one here represents my U. This little small green one, this lime green one right there, represents my V. Okay, so we can add the components. So if I even wanted to put in, uh-oh, this is going crazy, uh-oh, okay. So even if I wanted to put in like a -2U, it would be down here somewhere. So, and you can play with this and move it all around. So, you can kind of see what these vectors look like. Then I switched it around. I think I've got it right. Nope. Okay, so let's go and look here. So I drew these out for us. So I drew the component vector U and V. So I want you to see something, and then the red line there is the U plus V. Okay, so if I wanted to, this is called a parallelogram rule. So when I'm adding these components together, I wish I could. It keeps going to that. Here we go. Hold on. Let's copy this. Yeah. So, try my best here. I didn't do very good drawing. But we are going to make, if we finish this up, it's going to make a parallelogram. I tried my best to make. So that's going to be, oh, that red line's not even on the correct. I didn't draw it right. That's why that didn't work out. All right. So what the parallelogram rule tells me is that it's going to make a parallelogram by adding those vectors together. So your resultant vector is going to be one of the vertices of the parallelogram. So So it makes a parallelogram by adding vectors together. Okay. All right, so let's look at vectors in Rn. So n is in the real numbers. So we know that if Rn is in the reals, then Rn, so is the collection, so where we're not going to be in R2 anymore, so is the collection of all lists of order in tuples. So if it was R3, so then it would be triples. So this would be of n real numbers written as a column vector. Alright, so I'm gonna write it. It'll be a list of all the way up to n elements. So that's going to match however many elements I have. So if it was R4, then I would have 4 inside there. The 0 vector is a vector whose all of their entries is 0. So don't forget about a 0 vector. Okay. Alrighty. Alright, so algebraic properties of Rn. So this corresponds to properties of real numbers and pertain to vectors. We'll look at vectors in here. So to do these definitions, we'll call it vectors u, v, and w. And we'll have scalars c and d. So if I were to add two vectors together, that's the same thing as saying v plus u. So that's the commutative property. All right, grouping. So with addition, so if I were to add u plus v, if I grouped those and then added a vector w, it's the same thing as that if I say vector u plus vector v plus w. So remember, that's an associative property. If I add the 0 vector, it's the same thing as taking the 0 vector and adding u. It's just going to give me back my u vector, and that's the additive identity. Our inverse, so if I take u and I add to it negative u, that's the same thing as negative u plus u, and that does give me 0, so that's our inverse operation there. Distributive. So if I'm taking a scalar and I'm multiplying it times u plus v, that's the same thing as multiplying c times u plus c times v and adding those together. Same thing as if I take two scalars and multiply it times the vector u. It's the same thing as saying c times u plus d times u, and adding those together. And if I have my kind of associative property with multiplication, so it's the same thing as grouping and multiplying c times d, and then multiplying it times u. And then 1 times u will just give you your vector u. All right, so take a second, and I'm not going to work this one for you. So example 2, so take those vectors, so take this vector u and plot u, 2u, and a 1/2 u on the graph for me. Okay. So linear combination, so that it's a vector that's going to be defined by scalars and vectors. So the vectors so where we have each vector and a scalar, and it makes a linear combination. That should be a 1, I'm sorry, not an I. All right, where each one of the C's are my scalars. And all of the V's are vectors. So this is called a linear combination of the vectors with weights that are those scalars. So it's going to have weights. So this is what a linear combination is. We did one at the very beginning, so v1, v2 are the vectors with weights. C1, C2, up to Cn. So that's how it's going to be weighted. So I'm going to go back down there for a second, but these are weighted. So right here, this is a linear combination of my vectors. So this one's going to have a weight of a -2. This one's going to have a weight of a 4. Okay. Alrighty. So I want you to try to do number 3 for me, that example. And also try to do example 4 for me. Okay. All right. Let me know if you have any questions.